continue with computed design of digital filters. Last time we are discussing about a filter which is having both numerator and denominator polynomials, all right, minimizing the error. Now, this error that we are defining, the performance index, was basically the difference squared, all right, and summated. Okay. Now, this need not be always a square, it can be even any even power of the difference, e to the power 4 or e to the power 6 and so on. You can take any of these as the criteria. Anyway, today we shall concentrate on FIR filter. Okay. Now, in the normal FIR filter design, what we did, we took the Fourier series, okay, and then truncated it at the desired length. Now, it can be proved, it is there in all the textbooks. If you take the Fourier series coefficients up to any desired length, then that will be the best possible best combination of coefficients which will give you the minimum error. So, a rectangular window will give you minimum error, but we have also seen the effect of such truncated coefficients, truncated series will give you at the transition ripples. Okay. So, we wanted to reduce these ripples, that is the transition should be smooth as far as possible. So, we went for those window functions other than the rectangular window. Okay. But mind you, with those windows you may have little bit of reduction in the ripples, but the error will be more. Error is minimum with the actual Fourier coefficients wherever you truncate. So, we did not have any control over the distribution of the error in this entire span. Okay. We did not have any control. So, today we shall take up the other approach, that is, if we can make some flexibility, if we can offer in the passband and stopband tolerances, all right, or given a specified tolerance, whether we can approximate a polynomial, it will be a polynomial approximation which will give me best possible response. We will see what it will be like. We have, say, a function a to the power j omega, the amplitude function, as h e n, it is an even polynomial cosine omega n. Okay. H e n is h e minus n. All right. It is like this. It is an even function. You have seen in the tutorial class also, one of the problems was like this. So, this will be equal to h e 0 plus twice h e n cosine n omega. All right. In the last tutorial class we had that series minus 3 by 2, 1, 1 and so on. So, then we give a shift, so that actual h n, which will be equal to h m minus n, is h e n minus m by 2, is it not? We give a shift of sorry in that 9-point realization, we give a shift of 4 steps. All right. So, you obtain the final filter coefficients by giving a shift. So, let us define, say, q as m by 2, where your total length is m plus 1. all right. So, we had 9 point sequence. So, 9 minus 1 divided by 2 4. So, the shift was 4. So, basically those 4 coefficients will decide the polynomial H0, H1, H2, H3. Okay. So, H e to the power j omega will be A e to the power j omega into e to the power minus j omega m by 2. This is due to the phase shift. Now, we will take up this particular structure of the function to represent the magnitude function in terms of a polynomial in omega. This algorithm that we are going to discuss is known as Parkes-Mclellan algorithm. Okay. So, what it does is cosine n omega you can always write as a polynomial of nth degree in cosine omega. This we have seen in case of Chebyshev polynomial. If you remember, cosine n omega, we are writing cosine 2 omega is twice cos square omega minus 1, cos 3 omega and so on. So, it is basically that series. Therefore, that magnitude function, that amplitude function is a k cosine omega to the power k, k varying from 0 to say q. This will give me that H realized, H desired and H realized, there is a difference. So, that will be the error, all right. We will try to minimize that error in some sense. Minimization does not necessarily mean square sum should be minimized. Okay. We may be interested in minimizing something else. Let us see what could be other possible criterion. Now, the length, that is q, length is will be 2q plus 1, all right. So, length, then omega s, omega p, delta 1 and delta 2, these are the variables. Some of them are fixed, others are determined by changing okay. So, the amplitude varies between 1 plus delta 1 and 1 minus delta 1. This is omega p, this is omega s, this is delta 2 minus delta 2. Okay. So, the response may be varying like this. Sorry. Maybe like this. We are not really bothered about the transition. Omega p is fixed, omega s is fixed. This tolerance is given, this tolerance is given, and we may be given the length of the filter. So, the algorithm suggested by Park and Mclellan is omega p, omega s, these are fixed. Okay. At the desired value, at the desired frequencies. So, for a given L, we vary delta 1 and delta 2. Okay. Now, let us define an error function as now comes a weighting factor which is frequency dependent. So, we give different weightage to the deviation at different frequencies, it is not uniform. Earlier we are taking the desired response minus the realized response, square sum of this is not square of this error we are minimizing. Now, we are defining an error in terms of a weighting function, that means it is dependent on the frequency. Okay. Now, for a low pass filter, for example, for a low pass filter we are giving HD as 1 in this interval. Yes, please. HD is equal to 1 and 0 between omega s and pi. This is the desired response. That is it should be it can be like this. We are not putting in this error function, we are not putting any condition here. That means, this function will be quantified, this function will be measured only in these two subsets, all right. So, we define the weighting function as 1 by k in this interval 0 omega omega p and equal to 1 omega s omega pi, where k we are defining as delta 1 by delta 2. So, if delta 1 is more, we are having a factor 1 by k inverse of that. Okay. That means, we are giving less weightage to this deviation. Okay. So, that basically we are normalizing this, is it not? With this factor, if you see the error function will look like this. I will plot it here. The error function may be like this. Be like this. Okay. They are within the same bound, some delta. So, we are using Minimax criteria instead of squared error criteria, minimization of squared error. We are having Minimax criteria, which states, it is also known as Chebyshev criteria. That is, within the frequency band of interest, within the frequency band of interest, what is our frequency band of interest? It is the pass band and the stop band, omega is to pi and 0 to omega p. We try to find the frequency response to give minimum value of the maximum weighted approximate error. Okay. That is, we maximize this error, whatever is the maximum error, we try to minimize that. So, we try to find the frequency response to give minimum value of the maximum weighted approximation error. Okay. So, let us see what it will be like, or mathematically we can write minimize the function 0 n q maximum of E omega. Omega in this closed subset, F is the closed subset zero omega pi. Okay. Which means it is basically union of these two subsets. Zero omega omega p omega s omega pi. So, from H-E-N we will be determining H-N. So, if you have Px as a polynomial ak xk, k equal to 0 to q, and there is a desired function say dx, which is continuous on Fp, this entire range of frequency, then Ex is equal to Wx into dx minus Px. There is a polynomial that we have approximated to. The deviation of this function from the desired function multiplied by the weighting function we are defining as Ex, and we define Emax as maximum value of Ex. Okay. Absolute value of Ex, whatever is the maximum value, we call it Emax. For Px to be unique, we are trying to find out that Px which will be giving me minimum value of this Emax. Is the problem clear? We are trying to find out that Px is this coefficients basically Ak's, which will minimize this maximum value. So, for this condition, that is for Px to be unique, Ex must have at least q plus 2 alternations. This is the alternation theorem. we are going to discuss what is, that is q plus 2 alternations, that is q plus 2 values of xi, that is q plus 2 values of xi must exist in that range, that is x1, x2, x3. I should be able to get q plus 2 and exi must be okay exi minus exi minus 1 xi plus 1 equal to minus exi plus 1 equal to plus minus E max. Okay. What does it mean? You will have successive number of points x1, x2, x3, x4, all right, where the function will be alternating, all right. Okay, let me just show it, where it will be hitting the maximum value, plus maximum value or minus maximum value. That is the error function E. This is E max plus E max minus. So, you will have, it may not start from 0. So, this is x1, this is x2, this is x3. So, alternately there will be plus and minus, all right. You cannot have a situation like this, it will go to the extreme value, okay, and there will be at least q plus 2 number of such points. Mind you, this is in terms of the error, in terms of the error. So, let us see what it will be like for a type 1 filter. That is even symmetry and odd number of terms, all right, even symmetry and odd number of terms. So, in that case, if you remember, we had in an earlier class, the polynomial can be written as a k cos omega to the power k. We had derived these similar expression. So, after summing up, we can write in this form. Is that all right? For example, if you have h0 plus h1 cosine omega plus h2 cosine 2 omega and so on, I can always write this as h0 plus h1 cosine omega plus h2 cosine 2 omega can be written as twice cosine squared omega minus 1 by 2 and so on. So, finally, h0 plus minus h2 by 2. So, all these terms will be forming the first coefficient. Then you will have cosine 3 omega term will give you cosine omega also. So, that will be clubbed with those coefficients will be clubbed with h1. So, something into cosine omega and so on. So, you get a polynomial of this type. We are not really concerned about the relationship between h0, h1 etc. and ak, that is not required. So, dx is equal to 1 and 0 cosine omega p cosine omega and 1. We are making a plot. Now, we are trying to study px, okay, and this is minus 1 cosine omega s. Why minus 1? Cos pi, all right. So, this entire range 0 to omega p omega s to pi, what will be the value of cosine 0, 1, then cosine omega p. So, it will be lying between cosine omega p and 1 in this range cosine omega. Similarly, in this range it will be cosine omega s and minus 1. Okay. So, that time the desired function should be 0. E x, which is now cosine omega, should be w cosine omega d cosine omega minus p cosine omega. Okay. Our polynomial is in terms of cosine omega. X means cosine omega. The closed subset E p, the closed subset E p is basically union of the two subsets S1 and S2, where S1 means S1 corresponds to 0 to omega p and S2 corresponds to omega s, omega and pi, which means this corresponds to cosine omega p, cosine omega 1, and this corresponds to minus 1 cosine omega and cosine omega s. Okay. So, alternation theorem states, the alternation theorem states that for the unique function to exist, a set of coefficients a k, a set of coefficients a k in this polynomial cosine omega to the power k summation will correspond to the filter. This will correspond to the filter representing the unique best approximation, unique best approximation to the ideal low pass filter low pass filter with the ratio delta 1 by delta 2 fixed at k and omega p omega s fixed. You have omega p and omega s fixed, delta 1 by delta 2 ratio fixed at a value k, then E cosine omega will exhibit at least q plus 2 number of alterations on Fp. It can be more, alright. What can be the maximum value? Can it go to infinity? It should be at least q plus 2. What could be the higher value? 2q plus 1. What should be the maximum number of maxima and minima? That is, this error will be hitting maximum value and minimum value. How many times? If your order is fixed, suppose it is 9-point sequence, that means there are how many values? 4 coefficients, is it all right, or 5 coefficients? You can always normalize it, no, 1 plus something. Okay. Suppose we have 5 coefficients or 4 coefficients, then what should be the value of maximum value of alterations? The alternations can be, let us see how many points, q plus 3, q plus 4, let us see before we go to that, let us also just sketch what will be the functions like say Px for example. Let me take a little bigger page. This is x, this is Px. What will be the Px like? Px is cosine omega, all right. Px is basically P cosine omega. Minus 1, 0, this is cosine omega s stop end. We are assuming that omega s is such that its value is positive, it could have been negative also. Then pass band, okay. Then cosine 0 is 1. This is cosine omega p. This is 1 plus delta 1, 1 minus delta 1, this is delta 2 minus delta 2, all right. So, it will be like this, okay, sorry, it will be maybe let me produce it a little more. Let this be 1 here, going up, and this will be going down. If you remember the Chebyshev polynomial we discussed, beyond this range it will be going up. So, this is how Px varies. It should have been here. What will be the variation of k, rather the weighting factor Wx? It is from minus 1 to this omega s, it is at 1, and here it is k. This is Wx. Any question? And Ex, it will be too crowded. Ex, the error will be something like this. Say like this, say this is omega s, cosine omega s, this is x, and then again this is cosine omega p, this is 1, this is cosine 0. It may be like this, or it could have been this way also. What I mean that after multiplying by that weighting factor Wx, the error, modified weighted error is this, all right, that varies between +1 and -1. It is this function which is of our interest, all right. Is this all right? What we had expressed earlier, if you remember, X is sorry, this weighting function multiplied by this deviation. So, this deviation after multiplying by this Wx, which is k, I mean 1 by k and 1. So, we get a normalized error. So, alternation theorem states that optimum filter must have a minimum of q plus 2 such alternations. Minimum number of alternations will be q plus 2. Alternations equal to q plus 2. This is minimum. Let us sketch one or two typical examples. What are the possible values of alternations in a given set? Say you have q equal to 7, all right. Now, we are just going to sketch the original filter function, what it will be like. I can have starting with a maxima, okay, let me say this is omega s, it enters here, it may be ending like this at pi, this is pi. So, what are the frequencies at which it is hitting the maxima or minimum value in that specification? This is 1, 2. So, in this particular case, let us see omega 1, omega 2, omega 3, omega 4, omega 5, omega 6, omega 7, sorry, omega 6, omega 7, omega 8, omega 9, omega 10. So, it is 7 plus 3, all right, need not be 7 plus 2, minimum, mind you, I just wanted you to raise this point. Why should it be so many? See, these are also the border cases. If you talk about these specifications in terms of the error functions, these are hitting the maximum or the minimum error, is it not? So, though the function does not have an absolute maxima or minima here, but these are also the boundaries. Okay. Now, in an open set, how many, say a polynomial of degree q, how many maxima and minima will it have in the open set? Q minus 1, all right, and then you can have 4 extremes, 0, pi, omega s and omega p, all right. So, q minus 1 plus 4 extremes, that will be the maximum possible number of alternations you can have. So, it will be q plus 3. So, at least q plus 2 means at the most q plus 3. Is it all right? So, let us sketch one or two more possibilities. This is extra ripple case. Where we have 10 such alternations. You may have extrema at omega equal to pi only. That means it will not start with a minimum or maximum, it will start with somewhere in between and then it will be 1 2 okay, ending with a extremum at pi. Okay. So, here you will find it will be 1 less, that is q plus 2. It may start with a maximum, okay, and may not end with an extreme point at omega equal to pi, then also we will have 3. So, maximum possible is q plus 3, otherwise it should be q plus 2. Now, qth degree polynomial you are having dp by dx equal to cos omega, okay, we have taken cos omega equal to x. So, dp by dx cos omega is x basically to the power k summation. If we differentiate, it will be minus sin omega into k into ak cosine omega to the power k minus 1. Pardon? If I differentiate with respect to x, it will not be there. If I differentiate with respect to omega, it will be there. Yes. If I have dp by d omega, okay, it will be minus sin omega check whether you get this kind of a relation. The algorithm that we are going to have now is very simple, because we have already established this relation. Say w, say let us take any frequency w1, h desired, okay, minus that function a p, which we call the amplitude function j omega 1, equal to, this is basically the error function, should be minus 1 to the power I plus 1, okay. If you take any ith value, instead of taking 1 ith value, then I plus 1 delta. We have seen that normalized error is same, okay. So, any value if I want to calculate, it is negative of the previous value, or alternately it is minus 1 to the power I plus 1, okay. So, this equation I can write in a matrix form for all the frequencies. So, it will look like this. If you translate this into the matrix form, 1 x1 squared x1 to the power q 1 by w omega 1 1 x2 x1 x2 x3, these are the solutions, all right, those frequencies, that is cos omega 1, cos omega 2, cos omega 3 and so on, x2 square and so on, 1 by w omega 2 1 x q plus 2 x q plus 2 squared, so minus 1 to the power q plus 2 divided by w omega q plus 2. This side will have a0, a1 and last one will be delta equal to h desired e to the power j omega 1 and so on, h desired e to the power j omega q plus 2. So, x1, x2, x3 you have already solved, you can calculate a0, a1. Now, you will find there are similar algorithms for other types, that is type 2, type 3 filters, and programs are also given. You can, I would like all of you to try this simple problem with a bicquad, that is say B1 Z inverse, so 1 plus B1 Z inverse plus B2 Z to the power minus 2 divided by 1 plus A1 Z inverse plus A2 Z to the power minus 2 into it had fallen into K. Try by that grid search technique find out the filter H which will meet this specification. Okay. You can take a few standard functions, say maybe this one, take any frequency, say maybe pi by 3 and pi by 2, this is 1, all right. We are not putting any restriction on the tolerance at this stage. What would be the values of B1, B2, A1, A2 and K, such that you get this type of characteristics, all right. Minimize the error, minimize error square sum. Okay. And then try also this problem, that is for an FIR filter. This is for a general IIR filter which we discussed in the last class, and for the same one take delta 1 to be 0.03 and delta 2 to be 0.01. For these specifications, design a filter of length 6, q equal to 6 by this Parkes-Mclellan's algorithm, this one. Okay. So, I leave it to you as an exercise, and you submit it along with other problems that I had given you earlier, or some more problems I will be giving you maybe next week or so. Sorry, not next week, week after next. Okay, I think I will stop here about this computer-aided design. The other design that is left is based on FFT. I will just give an introduction to FFT. The DFTs that you have been computing, say we take points, n number of points. What will be the number of computations? How many additions, multiplications will be involved in this? Let us have an n point set, then see, for example, if I have a sequence xn, then x0 is, how do you compute? X0 into e to the power j 0 plus x1 into e to the power 0 into omega, and so on, you keep on writing. And in DFT, this steps of omega will be omega n, which is e to the power minus j 2 pi by n. Okay. This is a basic angle. So, you get x0 plus x1 into wn nk, sorry 1k plus x2 into wn 2k, and so on. So, how many multiplications are there? For computation of any xk, for computation of any xk, how many multiplications are there? This is multiplied by wn0, there is a multiplication here. So, how many such terms are there? N number of points, is not n points having n multiplications, and then for n number of such components. So, there will be n into n multiplications in total, is it not? You have to calculate capital X0, capital X1, capital X2. So, n such components will require n into n multiplications. How many additions are there? N into n minus 1, because additions will be just one less, n minus 1 additions. So, n into n minus 1s, so many additions. All right. Now, let us see if I have n by 2 number of points. Then how many multiplications are there? N by 2 squared, again n by 2 square. So, this plus this, so many additions, that means n square by 2. Okay. So, this is the number of multiplications. Additions similarly, n into n minus 1 by 2 by 4 and by 4. So, again added together it will be additions of this order. So, earlier it was n square, now it is n square by 2. Earlier it was n into n minus 1, now it is n into n minus by 2. So, we have reduced the computation burden. Okay. We have reduced the computational burden by halving the set and computing these separately, but then there will be also some addition operation when we mix them together. All right. So, that will not be, the burden will not be increasing again back to the same figure, it will be a little more. So, there is a substantial amount of reduction of computational labor if we can half the sequence length. If we go down further, we can reduce it further. So, how long can you go? So, if you keep on halving it, that means it should be the original number n should be an integral power of 2. Okay. So, if you have 8 points, I can halve it into 2 4s, then again each sequence of 4 can be halved into 2 point sequence. When it comes to a 2 point sequence, then it becomes very simple. What will be the FFT of a DFT of a 2 point sequence? Say H0, X0 and X1, these are the 2 points. Okay. Then what will be capital X0 and capital X1? X0 plus X1 and X0 minus X1, very good. So, it is simple addition and subtraction of 2 quantities, all right. So, we will start from this bottom end, we call it simple butterfly. If I have X0 and X1 as the input, the upper one will take X0 plus X1, the lower one will take X0 minus X1. Okay. So, this is a butterfly structure where addition and subtraction will result at the output stage. Okay. So, taking this butterfly to next higher level will be involving now complex multiplication and additions. Okay. How do you get minus and plus? It is basically W2, it is not e to the power minus j pi, all right. Now, if I am going for a 4 point sequence, then it will be e to the power j pi by 2, e to the power j pi by 2 will involve j plus j minus j plus 1 minus 1. Okay. So, in the next step we will have multiplication by imaginary and real numbers both. Next to next step it will be 45 degrees. So, these are the different multipliers that will creep in and we will have to keep on making additions and subtractions. So, in the next class we will take up this algorithm. Thank you very much.